with beams of electrons from the superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Good evening. Good evening. I'm Beverly Hartline from CBAF, and it's my pleasure to introduce tonight's speaker, Dr. Joel Levine from NASA Langley Research Center. Dr. Levine is a senior research scientist in the Atmospheric Sciences Division, which he actually founded and directs. He was born and raised in New York City, became interested in science when he was in 6th grade, and saw pictures taken with the Mount Palomar's 200-inch telescope of Mars and Jupiter. And he was so excited about what one could learn about other worlds than the Earth that he joined an astronomy club instantly and has been hard to separate from science ever since. He got a bachelor's degree in physics at Brooklyn College and a master's degree in meteorology from New York University, and in astronomy and planetary sciences as well. And he received his PhD in atmospheric sciences from the University of Michigan. Dr. Levine's areas of research include the origin, early history, evolution, and future of the atmosphere, the origin and life and the atmospheres of the planets. And he's the author and co-author of more than 150 papers and book chapters. He's also edited books, written textbooks, and received numerous awards and lectured in practically all of the continents of the Earth, with the possible exception of Antarctica. You haven't spoken there yet. One of the most exciting things he's been involved in the last couple of years is the television series Mission Earthbound. How many of you saw that when it was aired on PBS? He told me just before this program that series, in fact, has been nominated and is a finalist for an Oscar-like prize at the 37th Annual New York Film Festival, which is next weekend. And so he'll be going to New York to find out whether Mission Earthbound receives that prize. This is the first NASA program that's ever gotten that far in this prestigious international competition. Without further ado, I would like you to join me in welcoming Dr. Levine to talk about Earth on Fire, the environmental impact of global burning. That's you.
Is it?
Yeah, I think.
No.
Maybe.
I don't know. Yeah. It's certainly a pleasure to be here tonight at CBAF. Just about a month ago, Dr. Hartline came to NASA Langley and gave a very exciting talk about CBAF, and I'm very pleased to come back and hear and hopefully give an exciting talk about global environmental change. I want to thank you for the nice introduction. The only correction I'll make is the Atmospheric Science Division at NASA Langley I don't direct and I didn't found. I founded the Atmospheric Science Department at the College of William and Mary, and I direct that program. So just to set the record straight. What I'd like to do is I'd like to talk to you about some global environmental issues, things that are fairly serious problems. For the first time in the 4.5 billion year history of our planet, a form of life on our planet has the capability to alter the global environment. Now, this really hasn't happened. It happened once before. It happened about 3 billion years ago. 3 billion years ago, oxygen produced from photosynthetic activity by one-celled microorganisms on our planet changed the whole atmosphere. There's no oxygen in the atmosphere, and about 3 billion years ago, oxygen produced by photosynthetic activity by one-celled microorganisms began to build up in the atmosphere. And as a result, oxygen developed to be the second most abundant gas in the atmosphere, 21% by volume. And that was a case where a form of life altered the global environment, not a small regional local environment, but the global environment. And the next case, the next time that happened is right now. And the form of life that is altering the global environment is the human species. And that's what I want to talk about. But before I talk about the history of the Earth's atmosphere and how it's changed, I want to take you on a trip through space. And I want to begin the talk by showing what some of our planetary neighbors look like in the solar system, and then concentrate on the third planet from the sun, the planet that we all live on. So if we can have the lights. And what I'd like to do is take you on a tour and show you some pictures that 10 years ago I couldn't show you. 10 years ago we didn't have. And Dr. Hartline mentioned that when I was in the 6th grade, I saw some pictures taken with a 200-inch telescope at Mount Palomar, pictures of Mars and Jupiter in a science book, and I really was excited with those pictures. Well, in the last 15 years, we have sent spacecraft to visit every planet in the solar system except planet Pluto, the most distant planet. We have made measurements of the planets, their atmospheres, their surfaces. And what I'd like to do is start the talk by taking you on a very brief tour of the solar system. And we'll begin with this object, which is not the moon. This is planet Mercury. This is the planet closest to the sun. And the surface of planet Mercury looks like the surface of the moon because it's covered by what we call impact craters. Material from space, iron, stone material, meteorites have pounded the surface of Mercury over the 4.5 billion year history of the solar system. The sun, the Earth, the other planets, we believe all formed about 4.5 billion years ago. And what we're looking at is one of the most heavily cratered surfaces in the solar system. And we think that there's so many impact craters on the surface of Mercury because Mercury never had an atmosphere. One thing an atmosphere does is protects the surface from these chunks of metal and stone that fill the solar system. And sometimes if you look up on a clear night, you can see a shooting star. That's a bit of solar system material entering the atmosphere. And as it enters the atmosphere, it's heated up because of frictional heating. Most of the time, it burns up in the atmosphere. But if a planet has no atmosphere, the material is going to hit the surface. And what we're looking at is a very, very heavily cratered surface due to billions and billions of impacts over 4.5 billion years. Now, my talk is dealing with atmospheres tonight, and this is an indication that there's no atmosphere on Mercury. So since there's no atmosphere, we'll go to the next planet. And the next planet is very interesting. This is planet Venus. Now, Venus has an atmosphere, and it's much, much thicker than the Earth's atmosphere. In most textbooks, if you read the chapter on planet Venus, it says Venus is the twin sister of planet Earth. Now, let me tell you about this twin sister. The atmosphere of Venus is 90 times thicker than the Earth's atmosphere. The surface pressure at the Earth's atmosphere, as you know, is 1 atmosphere. The surface pressure of the atmosphere of Venus is 90 atmospheres, 90 times thicker, 90 times more massive. And the major gas in this atmosphere is carbon dioxide. 95% of the atmosphere of Venus is carbon dioxide. On Earth, carbon dioxide is 0.03%. And finally, there are thick clouds on Venus. There are clouds that may be 50 miles thick. We have never seen the surface of Venus from the Earth because of these thick clouds. And these thick clouds aren't water vapor clouds, the kind we have on Earth, but these are concentrated sulfuric acid. So look at the Earth's twin sister. Clouds of concentrated sulfuric acid, very large amounts of carbon dioxide, and a very, very thick atmosphere. Now, because of the large amounts of carbon dioxide and because it's such a thick atmosphere, carbon dioxide is what we call a greenhouse gas. I'll talk about greenhouse gases in about 15 minutes. But the surface temperature on Venus is so high because of the large amount of carbon dioxide, a greenhouse gas, that lead melts in a matter of minutes. And in fact, the Soviets have landed several spacecraft on the surface of Venus, and after 2 or 3 minutes, the instruments have gone dead because of the extreme temperature. The temperature on the surface of Venus on the Kelvin scale is in excess of 750 degrees. 750 degrees Kelvin because of the large amount of carbon dioxide, which is a greenhouse gas. I'll talk about it in a few minutes. So this is a very, very different type atmosphere than the Earth, an atmosphere of 95% carbon dioxide and about 5% nitrogen, surface pressure of 90 atmospheres. Let's continue our tour of the solar system and skip the third planet. The third planet is the Earth, and I'll talk about the Earth in great detail. But let's go out to the fourth planet. And the fourth planet is planet Mars. And Mars is still a different type atmosphere. The atmosphere of Mars is much thinner than the Earth's atmosphere. It's about 1/200th the thickness. And the major gas on Mars, like Venus, is carbon dioxide. 95% of the atmosphere of Mars is carbon dioxide. About 3% is nitrogen, and about 2% is argon. Now, 1 atmosphere pressure is equal to about 1,000 millibars pressure. And so at the Earth's atmosphere, it's actually 1,013 millibars. That's what 1 atmosphere is. On Mars, the atmosphere is only 6 millibars. And occasionally there are clouds in the atmosphere of Mars. Most of the time there are no clouds, and we can see right down to the surface. And what we actually see are some impact craters as well as some volcanic craters. And there's a polar cap where carbon dioxide condenses out of the atmosphere and actually ends up on the surface as frost. So this is planet Mars. Again, very different than Earth and very different than planet Venus. If we go to the outer part of the solar system, we come to a series of 4 planets: Jupiter, Saturn, Uranus, and Neptune. And all 4 of these planets have several things in common. They are very, very large. The diameters of these planets are the diameter of Jupiter is 10 times the diameter of the Earth. That means on the equator here, you could put 10 Earths, line them up. So Jupiter's is greater than the Earth's diameter. And these atmospheres have very, very thick atmospheres. And the gases begin to freeze out in the atmosphere. So the atmosphere has gas and frozen gas. And the composition of all 4 of these atmospheres, Jupiter, Saturn, Uranus, and Neptune, are very similar. The major gas in these atmospheres is hydrogen, molecular hydrogen, perhaps 90%. Helium is about 10%. And there are trace amounts of ammonia, methane, and water vapor. So these atmospheres are very different than the Earth's atmosphere, very different than the atmosphere of Mars and Venus. This is Saturn, and the general feeling is that the rings that surround Saturn consist of material from the early history of the solar system, primordial material that 4.5 billion years ago led to the formation of the planet. This is leftover material. But again, Saturn is mostly hydrogen, helium, small amounts of methane, ammonia, and water vapor. This is a photograph of planet Uranus taken by Voyager spacecraft. This is what it looked like before computers enhanced the picture. This is a computer-enhanced picture. You see slight detail, but in general, there's not much detail on planet Uranus. We can see some cloud structure. And again, the chemical composition is mostly hydrogen, some helium, methane, ammonia, and water vapor. And the most distant planet that we visited in the solar system so far, planet Neptune, and again, we're looking at an atmosphere that's mostly molecular hydrogen, H2, and helium. And those are the two lightest gases on the periodic table, hydrogen and helium, and small amounts of methane, ammonia, and water vapor. Clearly, the most interesting object in the solar system, probably the most interesting object in the Milky Way galaxy, which consists of 500 billion stars, and as far as we know, the most interesting object in the universe, and as far as we know, the universe is filled with galaxies, an infinite number of galaxies, each galaxy containing hundreds of billions of stars, yet the Earth is probably the most unique object that we know about, for the simple reason that the Earth is the only object in the solar system, the only object in the galaxy, the only object in the universe that we know supports life. And this life has been on the planet for a long time. Earth was formed 4.5 billion years ago. The oldest rocks we ever found are 3.5 billion years old. And rocks 3.5 billion years old already show microfossil evidence of life. So the oldest rocks ever found on our planet, 3.5 billion years old, show fairly sophisticated microbial life. So the feeling is life formed very early after the Earth formed 4.5 billion years ago. Earth is unique because it has life, and as I say, as far as we know, Earth is the only planet the only object in the solar system, the only object in the galaxy, the only object in the universe that supports life. Now, what's very ironic is life formed on Earth early in the history from gases in the atmosphere. Gases in the atmosphere, acted upon by atmospheric lightning, formed complex organic molecules, eventually forming amino acids, and life on our planet formed from gases originally in the atmosphere. Once life formed, the atmosphere protected life and nurtured life, because if we didn't have an atmosphere, the exposure of newly formed life to the harsh environment of space, ultraviolet radiation from the sun, would lead to the quick destruction of life. What's ironic is life formed from the gases in the atmosphere in the early history of the planet, and for 4.5 billion years, the atmosphere protected life on our planet from the harsh conditions in space. What's ironic is that over the last 100 years, life on Earth, the human species, for the first time has been altering the composition of the atmosphere, the chemistry of the atmosphere, as well as the global climate of our planet. This is a photograph that was taken by an astronaut who was born and raised in Virginia Beach, Ken Reitler. Ken Reitler was born and raised in Virginia Beach. He was a test pilot for the Navy. He's commanded 2 recent space shuttle flights, one about 6 months ago. The one 6 months ago was the first flight where NASA invited a Russian cosmonaut to fly on a U.S. spacecraft. Ken was the commander of that mission. Ken took this picture with a handheld camera out the window, and he was at Langely about 2 months ago and actually presented me with a photograph, and I made a slide of it. What we're looking at is we're looking at the Earth from an altitude of about 200 miles, and we're looking at the atmosphere. This is the extent of the atmosphere, and you can see this sort of luminous object above the surface of the Earth. This is the Earth's atmosphere, and the atmosphere is a key ingredient to maintaining life on this planet. And when you look at it from space, it looks like a very, very fragile layer surrounding a very, very large planet. And in fact, the atmosphere is a fragile layer. And over the last several decades, we have altered the composition of this fragile layer that maintains and supports life, as well as we've impacted the climate of our planet. It is very common to look in newspapers and magazines and see articles like the heat is on, how the Earth's climate is changing, why the ozone hole is growing, planet Earth, how it works, how to fix it. A few years ago, Time magazine, in a major departure, didn't pick a man of the year or a woman of the year. Time magazine picked a planet of the year. And the planet of the year was endangered Earth, planet Earth. So over the last out of the last several years, we've become aware of changes in the global environment caused primarily by the activities of the human species. And that's what I want to talk about. In particular, the two problems I want to talk about is why the ozone hole is growing and how the Earth's climate is changing. Now, these aren't the only two environmental problems that we're concerned about. We have problems of air pollution near the ground. We have problems of water pollution. We have problems of pollution of the Chesapeake Bay. We have problems of acid rain. There are a whole bunch of environmental problems. But these two problems have something in common. The ozone hole and the Earth's climate have something in common. The first is they're global problems. They're not regional, they're not local. They affect the entire planet. Pollution of the Chesapeake Bay is an important problem, but it only impacts the Chesapeake Bay. Air pollution in Los Angeles, smog, is an important problem, but it impacts Los Angeles Basin. These are two global problems that affect all countries, all continents, all regions of the planet. And the other thing that they have in common is that the solutions to solve these problems are beyond science and technology, and I'll explain. Because to solve these problems requires international cooperation of all of the countries on the Earth. So to solve them, we have to all get together and change the way we do certain things. So these are truly global problems. Both of these global problems that I want to talk about, the depletion of the ozone layer and global warming, the so-called greenhouse effect, have two things in common. The first thing is they're due to changes in the composition of the atmosphere, and those changes are due to human activities. Now, you all know that the atmosphere is 78% nitrogen, 21% oxygen, a little less than 1% argon. And then there are other gases. Well, what's so interesting is these other gases are the culprits in these global environmental problems. What's so interesting is the gases that are responsible for ozone destruction, and I'll talk about that in a minute, and the gases that are responsible for global warming, I'll talk about that in a minute, are found in the atmosphere at very low levels, and we call them trace gases. And let me tell you what I mean by trace gases. If I say nitrogen is 78% or oxygen 21%, what that really means is nitrogen, 78%, is 78 parts per 100. That's what a percent is, 78 parts per 100. Oxygen is 21 parts per 100. That's what 21% is. Now, the trace gases that lead to the destruction of ozone and lead to global warming aren't measured parts per 100. They're not even measured parts per 1,000. They're measured parts per million, parts per billion, and parts per trillion. So the gases that do that impact the chemistry of the atmosphere, the gases that impact global climate, are at very low concentrations, so low we call them trace gases, and the concentration of these gases are parts per million, parts per billion, parts per trillion. So they're very minute quantities, but because of their chemical effects and their radiative properties, they impact the global environment. One of the most important gases in the atmosphere is ozone. Now, you don't experience ozone on a day-to-day basis, but without ozone in the atmosphere, Seabath wouldn't be here, we wouldn't be here. For all likelihood, life wouldn't be here if it weren't for ozone. Let me tell you what ozone is. You know what a molecule of oxygen is. 21% of the atmosphere is oxygen molecules. An oxygen molecule, and that's what we're breathing right now, an oxygen molecule consists of two oxygen atoms that are chemically combined, that are bound together. So one oxygen molecule, which has a symbol O subscript 2, O2, consists of two oxygen atoms that are bound together. Now imagine we take an oxygen atom and add it to an oxygen molecule. Then we have ozone. Ozone's symbol is O sub 3. It has 48 atomic mass units. Molecular oxygen, the oxygen that we're breathing, has 32 atomic mass units. Atomic oxygen has 16 atomic mass units. So 16 times 3 is 48. Ozone has 48 atomic mass units. Ozone is unique. We've measured over 1,000 different gases in the atmosphere, but only ozone has a unique property. Only ozone has the ability of absorbing biologically lethal radiation that the sun gives off. 93 million miles away, the sun gives off radiation, light, heat, radiation at all wavelengths. And one component of radiation that the sun gives off is called ultraviolet radiation. Now, for those of you who are taking physics or chemistry, we're talking about radiation between 200 and 300 nanometers. That's the same as 2,000 to 3,000 angstroms. This is ultraviolet radiation. This is the radiation the sun gives off, and only ozone, of all the gases in the atmosphere, only ozone has the ability to absorb this deadly radiation the sun gives off. Let me say something about ultraviolet radiation. Ultraviolet radiation, when it interacts with eyes, leads to the formation of cataracts. When ultraviolet radiation interacts with skin, it leads to skin cancer. Ultraviolet radiation leads to diseases and illnesses of the human immune system. Ultraviolet radiation destroys crops, and ultraviolet radiation can penetrate to about 10 feet of water, from the surface to about 10 feet below the ocean, and actually destroy the marine life. So these are all the things ultraviolet radiation does. None of these are good. And fortunately, for those of us who live on the planet, the Earth is protected from ultraviolet radiation by ozone, this molecule in the atmosphere that consists of three oxygen atoms bound together. If we wanted to measure ozone in the atmosphere and see how it varies with altitude, this is what it would look like. This is the surface. This is 50 kilometers. 50 kilometers is about 30 miles above the Earth. So this is the surface, and this is 50 kilometers. And this is the distribution of ozone in the atmosphere. And what I want to point out is, notice most of the ozone in the atmosphere is centered at around between 20 and 30 kilometers above the Earth. And notice that it forms a layer. This is called the ozone layer. Most of the ozone is between 20 and 30 kilometers above the Earth's surface. Now, the other thing I want to mention is that atmospheric scientists have different names for the regions of the atmosphere. From the surface to about 12 kilometers, the region is called the troposphere. The troposphere is the lowest region of the atmosphere. It goes from the surface to about 12 kilometers. 85% of the mass of the atmosphere, 85% of the total mass of the atmosphere is in the troposphere. From about 12 kilometers to 50 kilometers is the region known as the stratosphere. The stratosphere only contains about 15% of the atmosphere, 15% of the mass of the atmosphere, but the stratosphere contains 90% of the ozone. That's why the stratosphere is so important. So 90% of the ozone is in the stratosphere, only 10% is in the troposphere. And that's why we're very concerned about the stratosphere. It's this ozone, 90% of which is in the stratosphere, that is responsible for absorbing deadly radiation that the sun constantly gives off and has been giving off for 4.5 billion years and will continue to give off for the rest of its life. Ozone is such an important gas that many years ago NASA decided to develop instruments to study the global distribution of ozone. And what we're looking at is a data set of the distribution of ozone, and this is from a satellite called Nimbus 7, and the instrument is called TOMS, Total Ozone Measurement Spectrometer, and this is October 3rd, 1979. And what we're looking at is the southern hemisphere of the Earth. The satellite goes around the Earth every 90 minutes, makes measurements, and in order to visualize the distribution of ozone, we usually color code the data. The unit that we measure ozone is called a Dobson unit. Dobson was an atmospheric scientist who first made measurements of ozone, and in his honor, the unit of ozone is called a Dobson unit. And what I want to point out is light blue is 250, dark blue is 350, and those are Dobson units. Ozone varies with latitude and with season, but in general, we expect anywhere above the Earth's surface for there to be between 250 and 350 Dobson units. It varies with latitude and it varies with season. But what we should see on these charts are light blue and dark blue. And you can actually see the continent, the Antarctic continent right here. Remember, we're looking at the southern hemisphere. This is one day in the life of ozone, October 3rd, 1979, measurements made with the Nimbus 7 TOMS instrument. And this is what the distribution of ozone looks like. Well, let me show you what the distribution of ozone looked like a few years later. Same satellite, Nimbus 7 TOMS, October 1st, 1983. And what we're seeing, light blue and dark blue, as we saw 4 years earlier, but there's one difference. Notice right above the South Pole, we have a different shade of color. If you can see the scale, it says 150 Dobson units. Well, this feature, this is the famous, or more correctly, the infamous Antarctic ozone hole. This was discovered several years ago, where at the beginning of every spring, and remember, in the southern hemisphere, spring begins September 23rd. The beginning of spring in the southern hemisphere, every year, ozone disappears over the South Pole. And this is the Antarctic ozone hole. It's a thinning of ozone over the South Pole. This is data with the same instrument, but now we've put the instrument, the NASA instrument, on a Soviet satellite called Meteor 3. And this was taken, this is data from October 18th, 1994, so it's the most recent data set we have. And notice this is the Antarctic ozone hole. It has gotten bigger. Here is Antarctic continent right here. The color scale is different, but we're seeing values. This is 100 Dobson units, 200 Dobson units. So within this Antarctic ozone hole, we're seeing approximately 50% decrease in ozone. Now, let me show you some more measurements of the Antarctic ozone hole and then talk a little bit about it. These are measurements made by not a satellite, but by ground-based observers in the Antarctic who go there every spring. And this maybe you can focus a little better. I don't know if I can focus. Yeah, I can focus it good. This is in the 60s, 70s, and 80s. This is 200, 300 Dobson units, and this represents values at the beginning of spring, the end of September, month of October. And notice that for about a 10-year period, ozone over the South Pole was about 300 Dobson units, a little bit more. And all of a sudden, in the early 70s, we got a significant decrease in ozone over the South Pole. This is a similar data set showing ozone decreasing from the 60s to the 90s. And here you see something interesting. Just as ozone is decreasing, we see another gas over the South Pole is increasing. And that gas, chlorine, is increasing over the South Pole. We now believe that the destruction of ozone over the South due to the reaction of ozone with chlorine. Now, let me tell you what a powerful reaction this is. One chlorine atom can destroy 100,000 ozone molecules. One chlorine atom has the power to destroy 100,000 ozone molecules. Now, and that's what we think is happening over the South Pole. Now, we further believe that these chlorine atoms get in the atmosphere and are produced from man-made chemicals called chlorofluoromethane, chlorofluorocarbons and chlorofluoromethanes, which are used in aerosol spray cans. Now, chlorine is not a natural constituent of the atmosphere. There are very few natural sources of chlorine in the atmosphere, but these man-made sources entering the atmosphere primarily through the use of chlorofluorocarbons and aerosol spray cans diffuse up to the stratosphere. In the stratosphere, sunlight breaks down the molecule, releases chlorine, and that one chlorine atom can destroy 100,000 molecules. Now, you're probably asking yourselves, why over the South Pole? There are not many aerosol spray cans in use over the South Pole. And that's true. There are not many people living in the South Pole. And the reason has to do with an interesting feature. About 15 years ago, a colleague of mine at NASA Langley, Pat McCormick, an atmospheric scientist, discovered something which he called polar stratospheric clouds, PSCs. What he found is that most polar stratospheric clouds occur over the South Pole in the winter, over the South Pole in the winter. Well, we now believe, to make a complex story short, we now believe that these polar stratospheric clouds recycle chlorine. After a chlorine atom destroys 100,000 molecules of ozone, it ends up in another form. Well, what polar stratospheric clouds do is recycle the chlorine and returns the compound back to active chlorine that destroys ozone all over again. Now, the reason that we have an Antarctic ozone hole and not an Arctic ozone hole is because we have most of the polar stratospheric clouds over the South Pole. And why do we have most of the polar stratospheric clouds over the South Pole? During the winter, the South Pole winter is about 20 degrees centigrade colder than the North Pole winter. And because it's colder over the South Pole, more polar stratospheric clouds form over the South Pole. So the reason we have an Antarctic ozone hole and not an Arctic ozone hole is because we have polar stratospheric clouds over the South Pole, because the South Pole winter is 20 degrees centigrade colder than the pole in the Northern Hemisphere. That's why this is a South Pole phenomena. Now, in a few minutes, I'm going to talk about some interesting aspects of this. Let me switch gears and talk about the other major global environmental problem. That's called global warming. And when we talk about global warming, what we're talking about is something called the greenhouse effect. And let me tell you what the greenhouse effect is. The greenhouse effect is the ability of certain gases in the atmosphere, and we call these gases greenhouse gases, to trap heat energy that the Earth gives off. The surface of the Earth gives off heat energy or infrared energy. If we didn't have greenhouse gases in the atmosphere, this heat energy would travel through the atmosphere and escape to space. But we do have greenhouse gases in the atmosphere. For 4.5 billion years, we've had greenhouse gases in the atmosphere. And the greenhouse effect has been here as long as the Earth has been here, and it's very important. And let me give you an example. The Earth is 93 million miles away from the sun. At that distance, the Earth should be at a certain temperature. The temperature the Earth should be at, the mean temperature of the Earth is minus 4 degrees Fahrenheit. In other words, the Earth should be an object with a mean temperature of minus 4 degrees Fahrenheit. Now, you know that water freezes at 32, and you go outside and see that water isn't frozen, except on cold days in winter, perhaps. And the reason for that is the temperature of the Earth is above minus 4 degrees Fahrenheit. If you went out with a thermometer, went from the North Pole to South Pole every month and took the mean temperature of the Earth, the mean temperature of the Earth would be 60 degrees Fahrenheit. 60 degrees Fahrenheit is the mean temperature of the Earth. But the temperature of the Earth, based on its distance from the sun, should only be minus 4 degrees. Why is the Earth 64 degrees Fahrenheit warmer? Because of the greenhouse effect. That from day one, 4.5 billion years ago, we've had naturally occurring greenhouse gases in the atmosphere. What we're concerned about today is that human activities are increasing the levels of greenhouse gases in the atmosphere. And let me show you what I mean. Over the last decade, if we look at the gases that contribute to the greenhouse effect in the atmosphere, 55% of the greenhouse effect is due to carbon dioxide, 17% due to chlorofluorocarbon 11 and 12. The gases that destroy ozone by releasing chlorine are greenhouse gases. Methane, another greenhouse gas, is responsible for 15% of the greenhouse effect. Other chlorofluorocarbons, 7%, and nitrous oxide, 6%. So these are the gases that impact the greenhouse effect. Now, one other important greenhouse gas, the most important, isn't listed, and that's water vapor. Water vapor is a very important greenhouse gas. The reason it's not on this chart is these are human-produced greenhouse gases, and water vapor, by and large, is not produced by human activities. The water vapor in the atmosphere is controlled by the hydrological cycle, by evaporation and precipitation. But these gases are all produced by various human activities, and I'll come back to that in a minute. Why are we concerned about the greenhouse effect? These are measurements from 1958 to 1988 that show levels of carbon dioxide. Now notice, carbon dioxide is measured in units of parts. This is 315 parts per million. This is 355 parts per million. These measurements were obtained at a station in Hawaii, Mauna Loa Observatory in Hawaii. And what we see is that there's a seasonal cycle of carbon dioxide. There's more carbon dioxide in the winter. There's less carbon dioxide in the summer, because in the summer, green plants take carbon dioxide up in the process of photosynthesis. But notice the long-term trend. Carbon dioxide is increasing in the atmosphere at about 0.5% a year. It turns out all of the greenhouse gases are increasing, and in 1985, the World Meteorological Organization, that's a UN organization, got together about 100 scientists, atmospheric scientists, and asked them to project out to the year 2100 the levels of greenhouse gases. And what we're looking at is the prediction from 1985 to the year 2100 for those greenhouse gases I showed you on the pie chart. Notice carbon dioxide will probably increase to about 900 parts per million. Methane will go from today a little less than 2 parts per million to about 10 parts per million. And the other greenhouse gases, chlorofluorocarbons and nitrous oxide, are also increasing. Now you can take a big computer and you can put these projections in a computer and you can calculate the future temperature of the Earth based on these predictions of greenhouse gases. There's a report that was published in 1990 called Climate Change. It was a report of the Intergovernmental Panel on Climate Change. And what they did is they took these predictions, put them in a big computer model, and did some calculations. And this represents, in the yellow envelope here, the temperature of the Earth out to the year 2050, which is less than 60 years from now, if you believe greenhouse gases are increasing at the rate shown on the previous charts. Now, what I want to show you is there's some uncertainty. Estimates range, and this is degrees centigrade, from 2 degrees centigrade to 5 degrees centigrade. In terms of Fahrenheit, that's 4 to 10 degrees Fahrenheit. So the computer predictions say by the year 2050, the mean temperature of our planet will be anywhere between 4 degrees Fahrenheit and 10 degrees Fahrenheit greater than it is today. And if this is true, this is a very significant increase in global temperature. Now, what impact does that have on those of us living on the Earth? Well, there are 2 things that I want to mention. The first thing I want to talk about is what happens when you heat up the Earth. Well, one thing that happens when you heat up the Earth is that you begin to melt ice and snow in the world's glaciers. There are glaciers all over the world. And when you heat up the Earth, you begin to melt ice and snow. The other thing which is relevant is that water is a compressible fluid. If you heat a compressible fluid, the volume increases. So when you heat up the Earth, 2 things happen. The ice and snow melt, and eventually that liquid water ends up in the ocean. And as you heat up the Earth, the volume of water expands. So what happens is the total amount of water in the world's oceans increase. This is a calculation on sea level rise. This is part of the IPCC, the Intergovernmental Panel on Climate Change report. This is out to the year 2100. These units are in centimeters, so if you like inches better, divide by 2.5 centimeters to an inch. And what this says is, by the year 2050, the mean temperature, the mean height of the world's oceans by 2050 may be 35 or 40 centimeters greater than it is today. A 35 to 40 centimeter increase in the world's oceans. And what that means is that land that's presently occupied by more than 250 million people will be underwater. So this is a concern, that sea level rise, which results from global warming and the compressibility of water and the melting of water, may lead to flooding of large land areas. Let me say something about where greenhouse gases come from and then summarize this whole thing. The general feeling is that greenhouse gases, and let's only talk about carbon dioxide, 55% of the greenhouse effect of human-produced gases, 55% of the greenhouse effect by human-produced gases is due to carbon dioxide. The general feeling is that carbon dioxide results from the burning of fossil fuel, from coal, petroleum, natural gas. But I want to show you a very interesting data set. This is carbon dioxide increase, the one I showed you a few minutes ago from Mauna Loa, from 1958 to 1988. Again, 315 parts per million to 350 parts per million. It shows the increase of carbon dioxide over that period. But there's another curve, a yellow curve, and it's very interesting. This yellow curve is the world's use of fossil fuel. Fossil fuel in coal, natural gas, petroleum. And notice that for about 20 years, the world's use of fossil fuel increased about 0.5% a year, which is just the rate of carbon dioxide increase in the atmosphere, 0.5% a year. But notice in the early 1980s, the world's use of fossil fuel leveled off. And why did it level off? For two reasons. The first is, in many countries outside of the United States, more electricity is generated by nuclear power as each year goes on. Nuclear power is not used in the United States as a viable source of energy since 3 Mile Island. In fact, there have been no new nuclear facilities put on board. But in the rest of the world, that's not true. France uses nuclear energy, Scandinavian countries, some countries get 2/3 of their energy from nuclear power. That's one thing. The second thing is fuel-efficient cars. We're driving cars today that get between 30 and 40 miles per gallon. 20 years ago, those cars got 8 to 12 miles a gallon. So because of fuel-efficient cars and because of a lot of countries generating electricity by nuclear energy, the world's use of fossil fuel leveled off. Now, what's surprising is if fossil fuel was the source of carbon dioxide in the atmosphere, why didn't we see a corresponding decrease in carbon dioxide with time? Well, there are several explanations, there are several possibilities, and one possibility is there may be another source of carbon dioxide other than fossil fuel. And we started looking at other sources, other possible sources, and what you're looking at now is a very interesting photograph. This is an actual photograph of the United States. This is a photograph taken from a spy satellite. I couldn't show you this picture 7 years ago. Well, I could, but we'd all be arrested. 7 years ago, this picture was classified, top secret. This is from a satellite called DMSP Block 5. It's a Department of Defense satellite. And what it shows is what the Earth looks like at night. And actually, if you look closely, you can see Seabath. You can see the building right here. And about 5 years ago, I got a call from Langley Air Force Base, the meteorology office, and they told me they had 40,000 pictures like this. Did I want them? And if so, come and get them within 24 hours. And I wasn't sure what they were, but I don't resist things that are for free. If you're a scientist, and Bev can tell you, whenever you get an offer of free equipment or free material, you take it and see what you can do. Well, we went over in a NASA van and we got 10 cartons of photographs, each 8 by 10. We have 40,000 photographs like this, and we didn't know what to do with them, so we hired some William and Mary undergraduate students at $2 an hour to study these pictures. And we found out something very interesting. Let me just show you what some of these pictures look like. This is a composite photograph, DMSP, of, I think, 40 different pictures. This is the continent of Africa. This is Europe, Western Europe, Eastern Europe. We're looking at Asia. This is an actual photograph from the Defense Department, from DMSP Block 5. And what we did is we analyzed different sections. And let's look at Africa for a minute. And you don't have to know much about Africa to know, well, first of all, you see a lot of bright lights. What our students at William and Mary found, and we published this in Nature magazine a few years ago, is that 90% of the time, the bright lights correspond to population centers of the planet. And let me give you an example. If we look from Boston to New York to Washington, the Eastern Corridor, it's very bright. That's because there are a lot of people driving cars, living in homes, and so on. So we found the obvious thing, that bright lights are associated with people. But let me tell you what was surprising. That only occurred for 90% of the time. 10% of the time, the bright lights weren't associated with population centers, and that was puzzling to us. And let me give you an example. Africa. The central part of Africa and southern Africa, this is an enlargement. And look how bright it is. This was puzzling to us for a few days, and Don Cahoon, a programmer scientist who works with me at NASA Langley, had an interesting idea. He said what he would do is compare two pictures of the same region taken 10 days apart. Remember, we have 40,000 pictures in 10 boxes, and what we did is compare two pictures taken 10 days apart, and what we did is we subtracted lights from one picture from lights from the second. If they were cities, then the lights would still be there after 10 days, right? Because we don't move cities. Cities stay stationary. And what we did is developed a computer program, digitized the pictures, and looked at all of these pictures the same area 10 days apart. And when we looked at Africa, at images taken 10 days apart, let me show you what we found. Every red dot corresponds to a light that was there, but not there 10 days later. So clearly it couldn't be a city. We don't move cities every 10 days. What we were looking at, what we found, are fires going on in Africa. In one night, we measured over 100,000 fires in Africa. So what we found out is that large areas of the earth are burning every night. Large areas of the earth in Africa, Southeast Asia, in Russia, in China, over Brazil. And for the first time, we used these pictures to estimate how much of the area of the earth is burning. And let me tell you what we found. If you looked in the scientific literature and tried to answer the question, what percentage of the land area of the earth burns every year? The best estimate was 1/100th of 1%. 1/100th of 1% of the land area of our planet burns each year. Our analysis of these data said not 1/100th of 1%, not 1/10th of a percent, but between 1 and 3% of the earth burns each year. Between 1 and 3% of the land area burns each year. And these are some photographs of burning. This is burning in Africa. This is savanna grassland. This is burning in tropical forests in Brazil, tropical forest burning. And what we did is we made some estimates using satellite data for the first time. And we came up with an enormous amount of burning going on. In fact, just in the tropical forest, 30 million acres every year, that's 50 acres every minute burning. Now, when you burn, you produce a lot of gases. And when you burn a forest that's been around for 100 years, you release in 5 or 6 hours 100 years worth of carbon dioxide that formed the tree and the plant and the vegetation. And what we did is we took our analysis of global burning and we estimated how much gas is coming off from burning of the world's forests and so on. And it's summarized on this chart. And I just want to point out that if you look at carbon dioxide, this is the amount produced by burning. This is the amount produced by all sources, which is fossil fuel plus burning of the forest. 40% of the carbon dioxide, we believe, this was for 1987, 40% of the carbon dioxide. And if you look at some of these other gases, carbon monoxide, 32% of the carbon monoxide And if you look down the chart, we think that burning is a very significant source of many of these greenhouse gases and chemically active gases. So let me conclude. I was told that we had to finish by 8 o'clock because that's when the students walk out because their teachers tell them they have to be here until 8, and then at 8 o'clock they leave. So let me summarize the talk, and let me say that those of us who are living on the planet Earth are affected by 3 global problems: the depletion of ozone, global warming, and I think global burning. I think that the ozone problem is now in the arena of international cooperation and regulation because the countries of the world have gotten together. Vice President Al Gore, on the 25th anniversary of Earth Day, this April 22nd, will announce a program geared for high school students called GLOBE, a global program involving high school students from 100 countries to begin monitoring and measuring atmospheric greenhouse gases. And for the first time, this problem of global environmental issue will become part of the curriculum in high schools. And so on April 22nd, you'll hear a major address by the Vice President of the United States talking about these issues and what you as high school students can do to get involved. And with that, I will stop the talk. Thank you very much.